Okay, so today we're going to look at electron configurations. And so each electron has its own address or set of 4 quantum numbers. And we write them as in this format where you have N, L, ML, and MS in parentheses here in that order. So if we want to write a possible set of quantum numbers for an electron in a 3p orbital, let's write down, like, what is N? N is equal to 3. What about P, or L? Not P. Well, L, so we have a p orbital, which corresponds to what L value? 1. Remember, S is 0, P is 1, D is 2, F is 3. So L has to be 1. So what can ML equal? And MS? Yep. Plus 1/2 and minus 1/2, always. MS is always that. So if I want to write a possible set of 4 quantum numbers, I would write 3, N has to be 3, L has to be 1, but then I can choose out of those 3, I can choose 1. What do you want to use? 0, okay. We'll use 0. And then MS would be, you could choose one of those. So plus 1/2. So there could be a possible set of numbers, quantum numbers, for an electron in that orbital. Yep, that's 1 electron. Right. So you'd have this 3 is saying it's in the 3rd energy level. The 1 tells us it's in a p orbital or p sublevel. It's in the 0 orbital, and it has a positive spin. So it's telling us those 4. When we get to rules for electron configurations, we'll think back to this, that you can't, no 2 electrons can have the same set of 4 quantum numbers. So you can't be in the same energy level, same sublevel or same orbital and have the same spin. If you're in the same energy level, sublevel, and orbital, those electrons have to have opposite spins. So one would be plus 1/2, one would be minus 1/2. Or maybe they're in, if they have the same spin, they have to be in a different orbital. So maybe it's 3, 1, minus 1, plus 1/2. And then that would be different. L. This is ML. Yep. So the electron configuration is actually just how the electrons are distributed, and we write this in this form where we have 1s, 2s, whatever it is, and then superscript is how many electrons are in that sublevel. So there's 1 electron in the 1s sublevel, which is going to correspond to hydrogen, that element. We can also do an orbital diagram, and actually right underneath the line there should be a 1s. You should always label what orbital it is. And there's 2 electrons here in the 1s sublevel, so that would be helium. And we have opposite arrows up and down because we have 2 electrons with opposite spins. So you can't have 2 up arrows or 2 down arrows because they have to have opposite spin. So these are some rules that we have to follow when we write out electron configurations. We're going to account for all of the electrons in an atom and show where each of those electrons are. So the Pauli exclusion principle is that there's no 2 electrons in an atom can have the same set of 4 quantum numbers, kind of what we just said a couple slides ago. The Aufbau principle is saying that the electron will fill the lowest level possible, which is why they're in ground state. They're in the lowest energy level possible. We're going to deal with ground state electron configurations. And we'll learn the order of filling. There's a couple different ways. I think the easiest that you'll find is we're going to use the periodic table as a cheat sheet. Hund's rule is that orbitals of equal energy are each occupied by one electron before another is added. So if we are dealing with like the 2p sublevel here, we have 3 orbitals, right? And 2 electrons can be in each orbital. But when they fill the orbitals, 1 electron will go in this orbital, 1 electron will go here, 1 electron will go here. Then the second electron will go in that orbital, second and second. So the second electron does not fill an orbital until each orbital in that sublevel has 1 electron in it. So it'll go 1, 1, 1, and then 2, 2, 2. Or in the d sublevel, you'd have each of the 5 orbitals would have 1 electron first, and then you would fill the second. And that's Hund's rule. So let's go through how they fill. So this is the lowest energy down here, goes up to high. So we don't just fill all the S's first and then all the P's and then all the D's. We're going to fill in order of increasing energy. So according to this diagram, we'll fill 1S, then 2S, then 2P, then 3S, then 3P, then 4S, then 3D, then 4P, then 5S, then 4D. That's going to be actually the order that we fill. It's just showing us how their energy levels actually relate to each other. Another way you can write this down, because that's probably the hardest way to remember it. Oh, you're going to fill electrons. Oh, and there's a mistake, I remember. So there's 2 electrons in the 1s. We can have 2 electrons in the 2s. Now the 2p can hold 6. This should fill one, like an up arrow, and then another up arrow, and another up arrow, and then fill that second one. So we should have an up, 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 and then the second one. So this sublevel is not completely filled right now. There's only 4 electrons when it can hold 6. So these 2 electrons may be electrons where they're shared with another atom and they're forming a bond. So these are where chemical bonds will come into play later. No. It has to fill up 2p before it can start filling 2s or 3s. So here's another way you can write it down and see how it orders. If you write all the s's down, then the p's and d's. If you go diagonally, I've filled 1s, then 2s, then 2p, then 3s, 3p, then 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s. And that's a pattern you can use to remember how to fill. I think you'll find that this is going to be the easiest, though, using the periodic table, where we're going to use blocks. This is called the S block. And if you see here, helium, which is over here, is part of the S block, so it comes over here as part of the 1s. This is the P block, the D block, and then the F block. So if we look up at the periodic table, we have the S block right here. The first 2 groups are the S block. The P block, groups 13 through 18 here. The D block, right here, the transition metals. And then the F block is the actinide and lanthanide series. Now think about the S sublevel. How many electrons are used to fill the S sublevel? Two electrons, right? 2 electrons can fill the S. So if we look at this and we count over in the S block, 1, 2, we'll be able to use this to count electrons also. How about the P block? How many electrons can fill the P block? 6. So if we count 1, 2, 3, 4, 5, 6, there's 6 there. D block should have how many? 10. If we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 across. And then F can hold 14. If we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we're going to use this to count how many electrons are in each sublevel until we get to the desired element, whatever it is. So let's do an example just to go through how we use this. So the configuration for magnesium. So we find magnesium on the periodic table, 12. So we need a total of 12 electrons accounted for. According to the Aufbau principle, we had to start at the lowest energy possible, which is at 1s. 1s is always the lowest energy. So we're going to just read the periodic table from left to right and just fill the orbitals as we come to them. So we're going to start here at 1s. We're going to count 1, 2. So we have 1s2. Oops. Thank you. 1s2. So we've gotten to neon or helium. What element comes after helium? Lithium. And we're at which sublevel? 2s. If we look at the numbers down the side, those are already written in, but that corresponds to energy levels. So 1s, 2s, 3s, 4s, 5s, okay? So we're at 2s, 1, 2, so we have 2s2. Then what comes after beryllium? Boron, and what sublevel would that be? 2p. One, and how many? We're going to count across. 1, 2, 3, 4, 5, 6. So we'd have 2p6. Then what comes after neon? Sodium, and that is what sublevel? 3s, and we count both because we're going to magnesium, so 1, 2, 3s2, and since we've reached magnesium, we stop there. So that would be the electron configuration for magnesium. A way you can check yourself is the superscript should add up to 12 because we know there's 12 electrons. So 2 plus 2 is 4 plus 6, 10 plus 2, 12. So we do have the right number of electrons. Do you guys have questions on that one? Let's try... Let me just make up one. Let's just try nitrogen. So if this is nitrogen, we start at the lowest energy level possible, which is right here, and that's what? 1s, and we count 1, 2, so 1s2. Then what? Lithium is in 2s, 1, 2, so 2s2. Comes after beryllium, boron, which is in what sublevel? 2p, and we count across. 1, 2, 3. We stop at 3 because that's nitrogen, so we would have 2p3, and that would be our final answer there. And we could check. We need 7 electrons. So we have 7 for our superscripts. Yep. So that would be correct. Okay, well, let's look at this. The electron configuration of boron is 1s2, 2s2, 2p1. So how many electrons, without looking at the periodic table, how many electrons are present in an atom of boron? 5. You just add up the superscripts. 5 electrons. What's the atomic number for boron? If we have 5 electrons, we have 5 protons, and the number of protons is the atomic number, so it is 5. Now the orbital notation is those lines and arrows. So the orbital notation for boron, we can just read the electron configuration here and then draw it out as lines and arrows. So the first one we have is 1s, and how many orbitals are in the s sublevel? How many orbitals? 1 orbital, and we have 2 electrons in that orbital, so we'd have 2 arrows. How about 2s? Still has just 1 orbital, right? And how many electrons are in that orbital? 2, so we'd have 2 arrows. And then p is next. So how many orbitals are in the p sublevel? 3, so we'd have 3 here. And we'd have how many electrons there? Just one, so we'd stop there. Now let's compare that to nitrogen, which we already said that was our configuration for nitrogen. If we have 2p3, we'd have everything up the same, but instead of just one arrow, we'd have 3, and this is where you need to use Hund's rule, and you just fill one at a time in each orbital. That would be nitrogen. Okay, what do we have next? Is it the iron one? No. Okay, let's just do another example. We haven't talked really about the D block, so let's do one that's in the D block. Oops, can't see yellow. So iron is in the D block. Now, when is the first time that we run into a D sublevel? What energy level? If n equals 3, we can have, well, if n equals 1, we can have just an S. If n equals 2, we can have S and P. When n equals 3, we can have SPD, right? So the first time we have a D sublevel is in the third energy level. So our energy level, our D sublevel here is going to be a 3D, because that's the first time we have a D sublevel. Even though this is 4S right here, we're going to have 4S, and then we're going to fill into the 3D, and then we'll fill 4P. Because the first D sublevel that we have is a 3D, not a 4D. And that's just how the energy increases also. Same with, so let's look at this next row. We have 5S, and then 4D, and then 5P. 6S, this would be 5D, but now look, we go from element 57 to 72. This is where the F block were to come into play. So the first time we get to an F block is when n equals 4, right? If we have n equals 3 was SP and D, when n equals 4, we can have SP, D, and F. That's the first time we can have an F sublevel. So the first F sublevel here is going to be 4F. So we would fill 6S, 5D, 4F, and then finish the 5D, and then go back up to 6P. So let's look at iron as an example. Iron doesn't have to do with the F block, but we do go into the D block. So let's write the electron configuration for iron. Oh, the blocks. So what's the lowest energy level that we start with? 1s. So we'd start at 1s, and how many electrons are in 1s for iron? 1, 2. Yep. So we have 1s2. What comes after that? 2s, 1, 2. So we'd have 2s2. And what comes after that? 2p, and then 1, 2, 3, 4, 5, 6. So 2p6 comes after 2p. Right here we're at 2p, 3s, 2. Comes after 3s, 3p, 1, 2, 3, 4, 5, 6. If you know that P is full because we haven't reached iron, you should know that it's already 6, because 6 is the maximum number of electrons P can hold. So you wouldn't necessarily have to count, but you can. Argon, then next is 4s, 1, 2. And then what comes after 4s? 3D, 2, 3, 4, 5, 6. Yep. So we go to 3D6. Okay, let's think about the orbital notation with the lines and arrows. We've already done S and P. What about a D sublevel? How many orbitals would there be? 5, right? 5. So if this is, yeah, if this is 3D, how many arrows would we need in iron? 6, right? So we'd have 1, 2, following Hund's rule, you have to go 1 at a time first, 4, 5, and then we'll put our 6th one in. Now this doesn't matter, you could have all down arrows first and then put an up arrow, that doesn't matter. I just usually put up arrows first. As long as they're all the same first, and then you'll put all the same in second.
So if you were doing Mercury,
Mm-hmm.
on the very last row, you'd have 6s2, and then would you go to, what would you do?
There's a couple different ways. He's saying Mercury. If we go with just the last line here, starting at 6s, we'd have 6s2, and then you can do 5d1, then 4f14, and 5d9. Or you can have 6s2, and you can count all of these together, 5d10, but don't forget to put your 4f14 in. So that either way would be fine. And actually sometimes, and I don't remember if your book does this, they go in order of energy level. Like they would list it as 4f14 first, and then 5d10, and then 6s2. Just because they go in order of 4, 5, 6. So either of those ways is fine. However you would like. I don't like it the last way just because I like writing it in order that you actually fill it. But I like adding all the D's together. So I would write 5d10 instead of 5d1 and 5d9. So now, speaking of Mercury, if you look at Mercury, that'd be a lot of electron configurations to write out, wouldn't it, if we had to start all the way back at 1s. So we use what's called the noble gas notation, where you use the noble gas core of the noble gas that comes before that element. And you put that element, the noble gas, in brackets. And by doing that, you're saying, okay, we're using the whole configuration for that noble gas, and then we're going to add on some stuff to it. So, for example, the Mercury. What's the noble gas that comes before Mercury? Xenon. So we put xenon in brackets, and then you would write 6s2, 5d10, 4f14. So you don't have to write out the whole configuration. What element would this be for? Argon. So we're using the whole configuration for argon, plus 4s2, 3d10, 4p2. Mm-hmm. Germanium, yep. Now really, when you're looking at what element this is, since these are all full, if we just focus on this 4p2 and we go up to the periodic table, find 4p and count 2, 1, 2, it'd be germanium. So you really don't have to go through the whole configuration. Everything should be full up until the last orbital, and then just check that one. So I think next is we're going to do some problems with iron. So we've already written out the electron configuration for iron, so I'll rewrite this here. Once this comes, there you go. So we have iron. 1s2, 2s2, 2p6. 6, right? 1, 2, 3. Yeah. So there was our electron configuration that we wrote out previously. So now the next question is the noble gas configuration. So what's the noble gas that comes before iron? Argon, yep. And then, so the electron configuration for argon is this whole part up to 3p, right here. And then what we need to add to it is this last part, the 4s, 2, 3d6. That's all you have to do for the noble gas notation. Because the first time we have a D sublevel is when n equals 3, SPD. If you think about our rules for if n equals 3, we can have from 0 to n minus 1. That's the first time we can have a 2 for our L value. 0, 1, and 2 is the D sublevel. Mm-hmm.
Those match up
Until the D.
Yeah.
Right. And that's because the first D sublevel that you can have, D is a L value of 2, right? L value of 2. So the first time you can have a 2 as an L value is if n equals 3. Because when n equals 3, you can have L values of 0, 1, and 2. That's the first time you can have 2 as your L value.
So the numbers on the side really don't, like, they're really not that important.
It helps with the S and P.
But they don't really.
They don't correspond. No, it's not like the whole periodic table is based on those numbers. Because we don't have a 1p either. That p is the first p sublevel, but we go by 2 because the first time we can have a p sublevel, p is 1 for an L value. You have to have an n value of 2 in order to get an L value of 1, 0 and 1.
But that matches up.
That it happens to match up, yes. Right. Right. Mm-hmm. Yep. Okay, there's a question on this iron problem. It says how many electron-containing orbitals are there? So we need to add up how many of these orbitals have at least one electron in them. So S has how many orbitals? 1. I'm going to write them above so we can add them, keep track of them. And this orbital has at least 1 electron in it. This orbital has at least 1 electron. It's S again. How about P? 3 orbitals, right? 3 orbitals, 3 lines. Does it have at least 1 electron on each line? Yes, so we'll write up 3 because all of them have at least 1 electron. How about this S orbital? 1, and it has 1 electron at least. The P, this one again, 3, S. Now this D one, let's check it. This is probably the one where it may or may not be completely, or have an electron on it. This is 3D. Oops. We have it would look like this. So do each of the 5 orbitals have at least 1 electron? Yes, so we can add those 5 to it. Because the p sublevel has 3 orbitals, 3 orientations. We're looking at the ML value. How many ML values are there? So this would be 5. So if we add these all together, get 15. 15 electron containing orbitals. Now the next question says how many of these are completely filled? Right, 4 of these are not completely filled, correct? So we take away those 4 and we'd have 11 completely filled. And then does the next one say how many unpaired electrons are there? 4 unpaired electrons. And then where are those electrons located? Yep, in the 3D sublevel. So they're in 3D. Does that make sense? Okay, we're going to do the same thing for zirconium, number 40. So you guys tell me what the electron configuration would be. Where would we start? The lowest energy level possible is 1s2. Then what? 2s2. 2p6. 3s2. 3p6. 4s2. 3d10. 4p6. 5s2. 4d2. Yep. So that would be the complete configuration, and then the noble gas configuration. Krypton is the noble gas before it. Yep. And so then after krypton is 5s2 and then 4d2. Now we have to answer those same questions here. So how many electron-containing orbitals are there? We should know that all of these are filled all the way up to the top, up to this last one. So I'll just fill in the numbers here so we can add them. But now let's check this last one, the 4d2. Holy cow, that's a big eraser. But that works pretty good. So we just have 2 electrons, so it would look like this. So are all of them full or have at least 1 electron? No, only 2 of them do, right? So we'll write a little 2 there. So now we add them up. This was 15, 18, 21. I did not spell that right. So 21 electron-containing orbitals. So the next one say how many are completely filled? 19. We take away those 2 because those are not completely filled. How many lone pairs, or how many lone electrons, unpaired electrons? 2 unpaired. And where are they? In 4D. And then I don't know if it asks, but how many empty orbitals are there? 3.
Why wouldn't there be
3 empty orbitals. How many orbitals are empty? Right. You still have the possibility of filling 8 more electrons, though. Okay, so tomorrow we'll kind of review this. We'll do, since we really haven't done a problem using F, we'll actually go through a problem using F. But this, I'll give this out to you. This will be due at the end of the period tomorrow, so we'll just kind of review it a little bit tomorrow, and then you have the rest of the period to work on this. On number 1 and 2, well, on number 1 for sure, I want you to write like what is N, L, ML, and MS, like all the possibilities, and then write out one of the possible set of quantum numbers that you could have. So what's N, what's L, what's ML, what's MS, and then write one of those sets, like where you have them in order in parentheses. Write a set. And then, oh, number 2, you're just supposed to list the possible values.